Hey everyone, I'm Nguyen-Tu, and this is Lab 1 of Physics 2211. The purpose of this lab is to analyze the motion of an observed object that is moving at the same speed without changing direction with physics principles in a computational model. In this lab, I will be using Newton's second law and the momentum principle. Newton's second law is force equals mass times acceleration that tells us the acceleration of an object is directly related to how much force is applied to the object. The momentum principle tells us that in an isolated system, momentum is conserved for any interaction between two objects. Incorporating these two physics principles in my model with the velocity update formula, obtained by dividing both sides of the momentum formula by the mass of the object, I can predict the motion of my chosen object over time. To complete this lab, I followed 4 steps. First, I recorded the motion of a ball rolling across the table in the positive y direction. Second, I imported the video into Tracker to track the position of the ball at set time intervals. Third, I edited starter code and glow script to model the observed ball's motion. Finally, I created and compared the position time graphs of the recorded ball to that of the model ball. After these steps, the main result of my lab is that there's evidence my observed ball did not have net zero forces acting on it since its position changed at a faster rate than that of its predicted change of position under constant velocity conditions in my model. Shown here is Tracker analyzing the recorded observed ball video for this lab. In the observation video, the system is the Waymo Super Ball and the surroundings of the table and trifold roller. From Tracker, the initial conditions are position being 0.001739 meters in the positive y direction, velocity being 0.380068 meters per second in the positive y direction, and time being 0 seconds. For the assumptions used in my model, I assume that the net force acting on the ball is 0 newtons, with air resistance and friction both having a negligible effect, and that the table surface is perfectly level. Shown here is the GlowScript VPython code behind the model for this lab. I have 3 variables that stores the ball's current position, trail, and origin respectively colored blue, green, and yellow in the model. As for graphs, there are 2 created, being a position time graph and a velocity time graph. In this section of the code, the initial conditions of the observed ball mentioned earlier are described in code: the mass, position, and velocity. The mass of the observed ball is estimated to be 0.022680 kilograms from Google. The ball's position and initial velocity are both in vector format, with the y component being the second number in their respective vector. Time is set to 0 seconds, and the change in time is set to 0.016667 seconds, the change in time between each of the recorded measurements from the observation video. In this section of the code, with a while loop, I am estimating the position of the modeled ball at each of the time intervals that the ball in the observation video has data recorded. Fnet is set to 0 in vector format because of the earlier assumption that no significant forces are acting on my system. The ball's velocity is updated with the velocity update formula to calculate the change in velocity after each change in time. Similarly, the ball position is also updated by multiplying the calculated velocity by the change in time to get the ball's change in position and adding that to the ball's previous position. Time is updated by adding the change in time to the previous time. As these prediction calculations are made, the modeled ball's trail is updated to reflect the calculations, and the calculations are recorded into the position time graph and the velocity time graph. Also, the values of time, ball position, and ball velocity are printed to the console for easy transfer to Google Sheets for the analysis. Shown here is the resulting model with the position time graph on the top right and the velocity time graph on the bottom left. In this lab, there are sources of error, and I'll focus on the 2 main ones. The first is that the table might not be perfectly level. If this is the case, the gravitational force of the Earth acting on the observed Waymo ball would not be negligible and cause the ball to slightly speed up or slow down depending on the slope of the table. The second is that air resistance and friction might not be negligible as was assumed. If this is the case, Fnet would not be 0 and the ball would slightly slow down. Now for the discussion part of this lab. So what are the similarities and differences between the observed data and the model predictions? In both the observed and the model, the slope is roughly straight. According to Newton's second law, this means that there was not a force constantly influencing the balls in the positive y or negative y direction. That being said, since the observed ball's curve deviates higher than that of the model ball's curve, there is evidence that there was some change of velocity after the initial point of the observed ball's motion. Since the momentum principle tells us that momentum is conserved, this means that there is evidence that the net force acting on the observed ball was not completely net zero after the initial point, and, according to Newton's second law, that the observed ball experienced an acceleration in the positive y direction, since the observed ball's slope is steeper than that of the model. In my model prediction, I chose the orientation of my axes to have the positive y direction align with the direction that the observed Waymo ball was traveling. What would happen if I had flipped my axis from the positive y direction to the negative y direction? If I had done this, the magnitude of the observed ball's velocity would remain the same, but the direction would be in the negative y direction instead of the positive y direction. The position time graphs for both the observed data and the model predictions would be downward sloping and look like the current graph but reflected across the x-axis. Also in my model prediction, my observations were predicted well because I set the net force equal to 0. Having a net force of 0 means that for every force pointing in one direction, there exists one or more forces with components pointing in the exact opposite direction that sum to equal the first force in magnitude, canceling out the first force's effect on the system. Therefore, unless my system is in a perfectly controlled environment where all the interactions can be observed and measured, it is impossible to completely know how many pushes and pulls are added together to give a zero net force, but it is possible to point out the most likely significant forces like gravity with the Earth, air resistance, and friction against the table.